2600 terabytes, whatever. So when you see the sun here, you see these big loops. Those are big loops of tangled magnetic field. And the reason you can see them is they trapped the plasma, the glowy stuff of the sun in them, and that makes them light up. So kind of like elastic bands, each one of those loops has a certain amount of tension to it. And because the sun itself is moving around and all that material on the surface of the sun is moving, you get some of those bands snapping with time. And when they snap, they send all the stuff that is trapped in them, all this loopy stuff, not only out into space, but down onto the surface of the star where it heats up the star itself. And so it makes that part of the star get brighter for a little while, and it also sends material flying out into space, which you'll see momentarily. So this kind of stuff is actual like parts of the sun. It's not, you know, like giant chunks of it or anything, but it is material that is what the sun is made up of that streams out into space, and sometimes it ends up here at Earth and makes part of our atmosphere light up in the aurora.
Could you give a size comparison of the Earth to that?
The Earth is like as big as my fist. Yeah, so there, with that previous thing, it's about this big. Yeah.
What about an observing strategy of staring at a particular tile as long as you can? Do you do that rather than just these quick snapshots of your...
Yeah, we actually have talked about doing that. So most of the time that LSST operates, it'll tile over the sky and do these snapshots. But we also have these like special surveys or mini surveys that it does the rest of the time. So one of those can even be what we've all been calling in the collaboration movie mode, where we just pick part of the sky and stare. And that allows us to get down to fainter depths very fast, and we also get faster cadence or closer together observations. So yeah, that is definitely one of the things we're considering. There and there and there. Oh, wait, hold on. You're three, sorry. There's one behind you with the mic.
So you guys were talking about how this is going to be the most revolutionary thing since the Hubble telescope, and I know that a lot of the reason those images from Hubble are so good is because it's actually in space and there's no atmosphere between it and what it's looking at. So I was wondering why the decision was made to put this one on Earth and why it's still going to be more revolutionary than other observatories.
So my point wasn't that it's like more revolutionary than the Hubble. It's that it's a different way of doing astronomy. And so in some sense, it's better to think of it as being complementary to the Hubble. The Hubble was transformative for the way that we think about images, in no small part because it is in space and we could get those beautiful crisp images and observe wavelengths of light that don't reach to the atmosphere here on Earth. But we also have, in the same couple of decades that we've had the Hubble, we also have incredibly rich resources here on the ground, here on Earth, of telescopes that do complementary kinds of things. So the LSST is the flagship for ground-based or Earth-based observing for the next decade. But we also have all of these other observatories that are going to go up in space. So kind of the next successor to the Hubble is the James Webb Space Telescope, which is an infrared telescope that will live out in space. One of the neat things about having something like LSST on the ground while you have those space-based observatories is that you can use them cooperatively. So you can observe the same kinds of things and learn complementary kinds of information to get crisper images than you would be able to from the ground. So one of the chief motivations for doing something like a ground-based survey is that it's way cheaper